Section 5.3, Evaluating Definite Integrals, page 1. So we've learned that the integral of f of x dx from a to b is represented as the net area of the curve between a and b, and also that the integral that we just discussed can be approximated using rectangles. And obviously the more rectangles we use, the better the approximation. So to use as many rectangles as possible, we said we're going to take the limit to get infinite rectangles, an unlimited amount of rectangles, and instead of getting approximately close, we should basically get the exact value. So in this section, we're going to evaluate definite integrals using that definition of going to an infinite number of rectangles that was originally discussed in section 5.2, and then we're going to learn the shortcut that you may already know. So for the fundamental theorem of calculus, we've already discussed number one, that if we were looking at the integral from a to a point along the goal of reaching b, then we've got a particular way to discuss the derivative of the integral of the function. But now let's talk about fundamental theorem calculus part 2. The integral of f of x dx from a to b can just be evaluated taking the antiderivative evaluated at b and the antiderivative evaluated at a and subtracting the difference, assuming that an antiderivative exists. And this kind of just restates that. Often you may see the integral of f of b, I'm not saying that well, but is written out, maybe with just kind of we're taking the integral and it's going to equal f from a to b. Okay, so let's go ahead again and talk about part 2. And we're going to take this particular problem and we're going to solve it 3 ways. The first way is to evaluate the definite integral, referred to as definite because we have an a and a b value. It would be an indefinite integral if we did not. And we're first going to solve it geometrically, which means shapes. We just discussed rectangles, but as we graph this particular problem, we'll discover that a triangle is better than a rectangle. So to evaluate it geometrically, I take the function 4 minus 2x, and I really prefer to rewrite it where the 2x stays negative, the 4 stays positive, but by writing it in descending order of exponents, it follows the y equals mx equation of a line format, where m is the coefficient of the variable, and if you think of slope as rise over run, we have negative 2 over 1. B is the y-intercept, and so we have a y-intercept of 4. And then I'm going to go down 2 over 1, down 2 over 1, and I can just keep repeating this. Because we're evaluating the integral from 2 to 5, I have this imaginary line over here at 5, and so when I draw my line, I kind of only need to go that far. Now, when it comes to shading, you might be tempted to shade these 2 triangles after doing quite a few repeats of problems in the previous section. But remember, we're only going from 2 to 5. So I only need to graph between 2 to 5 and my line to the x-axis. So I end up with this triangle over here. If I'm going from 2 to 5, I'm going a distance of 3 across. Visually, maybe you could see that I went 6 units down, but it's okay if you don't, because what we're going to do is we're going to take this equation, or really its original format, and we're going to plug our x value of 5 in, and 4 minus 10 is negative 6. So we have clarification that we are 6 units down. I chose to do a negative with the 6, but since distance could be absolute, even if you used a positive, you would just need to remember that for your answer, you're below the x-axis and change it to a negative sign. Using the formula for the area of a triangle and my base and height, I have that geometrically, the integral of this function from 2 to 5 is negative 9. I said we're going to solve it 3 ways. Here is the second way, where again, I'm going to get negative 9. The second way I'm solving it is to use the definition. remembering that the definition for the definite integral can be found as the limit as n goes to infinity of rectangles within the function, where f of xi is the height of each rectangle, delta x is the width of each rectangle, and we need to add up those rectangles from the beginning point of 1 to n, where this kind of goes through each of the xi columns of our rectangles. Usually when we do this, we start with delta x being the distance we're integrating over, divided into how many triangles we wish to have. So we can see from our problem that b is 5, 2 is a, but we were never told which n we needed, so we're going to just have to leave n as n. The width of each triangle is going to be 3n, where really, remember, we want infinite triangles, but we'll leave it as n for now. We're going to be taking the limit of the function evaluated at each column point, whether it's left, right, midpoint. So x is defined as your starting point of the range of numbers, the interval of numbers, plus whatever iteration of columns you're through, stepping by that width of each rectangle. So for us, we know we're starting at 2, and we don't know how wide each rectangle is, but generically we're saying 3 over n is the width of the rectangles. And so the function is going to be evaluated. The height is going to be determined by this equation. So again, taking that beginning piece of the definition and working with the right side of the definition, we're taking the limit as n goes to infinity, oops, there's no n there, of the summation from 1 to n of the function evaluated at xi. So remember, our particular function, I'm going to scroll down there, was 4 minus 2x. So here is 4 minus 2x, but we said x is going to keep changing according to the pattern 2 plus 3i over n. And the formula says you're going to multiply by the width of those rectangles, delta x, which we had previously defined to be 3 over n. So what I need to do is clean up everything that's happening here. I can distribute that 2 to the x values to get my minus 4 minus 6in. But of course, I now have a positive and negative 4 that are going to add off to 0. When it comes to these terms, even though the summation, we know we can factor the width of the rectangles out, the formula doesn't start with it factored out. So really what I'm going to do is just multiply negative 6i times 3 to get negative 18i. I'm going to multiply n times n to get n squared. And then I'm concerned with the summation of this. But remember, it's only changing based on I. So we're treating everything that's not I, the negative 18 n squared, as a constant. And we know from our summation rules that we can bring a constant out front. So now I'm looking at this formula where I'm focused on the summation from I equals 1 to n of just I. But we learned that the sum of I in that format is always going to be n times n plus 1 over 2. So I can really write this piece as just the final sum of all of those I values. I'm still taking the limit of this, but there's some math I can do. 2 will go into negative 18, negative 9 times. N will cancel with an n in the denominator once to give me a single n in the denominator. And so I could go ahead and distribute that 9 out to get this equation. And now I'm ready to take the limit as n goes to infinity by actually plugging infinity in to wherever n is. So this is really just infinity in the numerator because subtracting 9 is minimal, doesn't have an impact. The denominator is infinity. And because I have infinity divided by infinity indeterminate status, I can go ahead and use L'Hopital's rule to continue to take the limit, where I take the derivative of negative 9n to get negative 9 times 1, minus 9, whose derivative is 0, so I didn't even write anything, and n, whose derivative is 1. So I really am taking just the limit of 9 And so therefore there is nowhere to plug the infinity in. I am just going to have -9 as my answer, the same as part A.